Project 3.1.3, CHUMP, Arithmetic and Logic Unit. The third stage of CHUMP incorporates a device that performs the logic and arithmetic operations that are stored in the EEPROM devices from the previous project. The multiplexer or data selector is also introduced in this stage. This device is used to determine whether the program operates with a value from RAM or a value created by the program EEPROM.
So here you can see a multiplexer demonstration circuit and an ALU demonstration circuit. So looking at the multiplexer demonstration circuit, we can see 4 outputs and 8 inputs, each which are held high in a normal state and turned low with this switch. And this switch, which changes the state of the output. So if I just flick it, it'll produce a different output according to the switches over here that correspond to this output. You can also see right now that it's flashing, and that's because the strobe pin is wired to a clock pulse, which is fed on this rail over here. And so what I can do to change that is just move this wire and connect it to ground, and then it'll just stay solid, which it'll normally be on the final CHUMP build. Now we can mess around with some of the switches on this multiplexer to see what it's really capable of. So if I just alter some of the switches, currently it's in low state, so every even numbered switch here, 2, 4, 6, and 8, will directly affect what is shown here, and every odd numbered switch will not. And if I change that, now every odd numbered switch will affect it, every even numbered switch will not. So let's see this in action. So I'm going to flick some odd switches right now. This should directly affect the output over here. So now I've just altered the output because I've switched some of the states on these odd switches. If I change some of the even switches like this, nothing's going to happen. But if I were to switch it, we'd see a different output from before. Exactly. So that is the multiplexer demonstration circuit. Down here we have the ALU demonstration circuit. So we have these 5 LEDs showing the outputs. These red ones show the outputs on F, and this shows the Z flag, or the A equals B output. These 4 SPDT switches represent the system select inputs, and these 2 represent the M and CN, or mode and carry inputs. And what these switches do is they determine the operation that takes place within the ALU to determine these outputs. On these inputs, we have A is equal to 10, so binary 1010, sorry, A is equal to 12, binary 1100, and B is equal to 10, binary 1010. So right now, all of these operations are set to low. So mode is low and carry is low. So it's an arithmetic operation with carry, because carry is inverse logic. So that would mean A plus 1. This is shown. So A is 12 plus 1 is 13. 1101, that's 13. So if we were to change a couple of these things, so first let's try changing the mode. In the logic mode, which is when mode is high, the arithmetic carry bit does not matter. So this should be not A, so it is not A. So in a normal A output, these 2 would be high and these 2 would be low. That's inverted. Let's try a couple more. So I'm going to set it to F is equal to B, which is again a logic output, and that would be these switches high, low, so high, high. That's B. That is equivalent to the value B on the inputs over here. Let's set it to A and not B, so low, high, high, high. This is low, these are all high, and that's a combination of A and not B with that operator. And this operation works in logic mode and arithmetic mode with carry. So if I change this, the output's going to be exactly the same. Without carry, it's going to be this value minus 1. So we should see these two LEDs light up and this one go out like that. The next thing is f is equal to 1. So that's a logic function. But when f equals 1 in logic, that's logic 1. So all of these will be high. So that would be mode is high and these are high. These are inverse. So this is f is equal to 1. And a special thing that happens when all of these outputs are high is this output becomes high. And this pin is technically called A equals B, but that's not an accurate description because it doesn't come on when A equals B. In fact, A and B do not equal each other right now. It comes on when all the F outputs are high.
If we look over here on the CHUMP diagram, these components are located in the center, right side of the diagram. As discussed from the previous project, the C flag leading into the ALU is a reference for 6 pins, all the S pins, M, and CN. These all come from the control ROM. The Z flag on the ALU is wired into a NAND gate that feeds into the load pin of the program counter. This allows it to reset the count to a value that comes through the multiplexer on a given instruction. Thanks for listening.